So let me just rewrite this on another page. We are finding the limit of f of x minus f of a over x minus a as x does what? Approaches a. Now, let's say that h is equal to a minus x. If h is equal to a minus x, and we're going to substitute h into this, then what that's going to give us is we're finding the limit of f of x minus, looking at this, a would be equal to h plus x, so it would be f of x plus h all over negative h, and we're saying that h is approaching a, so we're going to end up here with h approaching 0 because h is equal to a minus x, and x approaching a suggests that these would end up giving, this difference would end up giving me 0. So we're finding the limit of f of x minus f of x plus h all over negative h as h approaches 0, which in effect gives us the limit of f of x plus h minus f of x all over h as h approaches 0. So what we call this limit is the difference, D-I-F-F, difference quotient. And this is something that is extremely important for you to remember. You are finding the instantaneous rate of change. And in order to find the instantaneous rate of change, you have to use this. You have to use this expression, the limit of f of x plus h minus f of x all over h as h approaches 0. In the end, we are going to get a number. What that number is the gradient of the curve at that point. It is the gradient of the tangent to the curve at that point too. And we call this limit, the constant that we get upon finding this limit, the derivative. We call it the derivative, the first derivative. And we represent it by saying f prime of x. We also say dy by dx. And we also say y prime. So when you hear people talking about differentiation, what they're talking about is a way, or the way, of finding the instantaneous rate of change, the rate of change at a single point. And the very definition of differentiation is, as I said before, again, I cannot emphasize this enough, the limit of f of x plus h minus f of x all over h as h approaches 0. That is the very definition of differentiation. Now, before we close, since the derivative, as we can see here, is actually the limit of a function, it is safe and reasonable and logical to conclude that where a limit does not exist, then the derivative does not exist. And we learned when we were doing limits and continuity that a limit does not exist at a point of discontinuity. So we cannot find the derivative at a point of discontinuity. So that's point 1, that the derivative does not exist at a point of discontinuity. The limit also, no limit exists at a vertical tangent line. And so in this case, the derivative would not exist at a vertical tangent line. That is, when I say vertical tangent line, I'm making reference to some asymptote and a function that is approaching infinity. So the limit would not exist at that point, and as such, the derivative would not exist at some vertical tangent line. And lastly, the curves that I am about to draw here we have what is called a kink, and here we have what is called a cusp at the points right here. Those are some odd points. And functions that have kinks or cusps would not have the derivative existing at those points. So for example, one function that comes to mind readily that has a kink would be mod x. And mod x the derivative of mod x does not exist at x equal 0. So yes, so keep those in mind. Those 3 points, those 3 conditions that render the derivative of a function, the instantaneous rate of change of a function at that point, non-existent.